Hi, my name is Pei Yun. Today I'm going to talk to you about our work on learning to optimally segment point clouds. Today, most autonomous vehicles perceive the world by capturing streams of dense point clouds with the help of LiDAR sensors. Currently, practical solutions often make heavy use of perceptual priors, such as geometric maps that have been built offline. These maps are often used as part of pre-processing to remove points from the background. To achieve instance-level object perception, existing pipelines often run clustering on the foreground points. Here we show the results of Euclidean clustering, also known as connected components, with a fixed threshold. As we see in the results, it tends to merge pedestrians into one big segment, which we call under-segmentation. This suggests the threshold epsilon, which is used to connect any points within such a distance, is too large for segmenting point clouds of pedestrians. Here, we try a smaller threshold. Now pedestrians are better separated, but the car on the left side is broken apart into multiple segments. Such segmentation error is also known as over-segmentation. These evidence suggests that the best epsilon varies from situation to situation, and there is no such one parameter that fits all situations. We propose an approach that can adaptively choose the threshold for each situation based on a data-driven model of objectness. To start, we reorganize the segmentations produced by Euclidean clustering with different thresholds, and importantly, in a hierarchical fashion. Each local segment is represented as a node in the hierarchy. We propose to learn a data-driven model to predict the objectness of each local segment. In this case, we choose PointNet++. First, we need to define the ground truth objectness. The red dots represent the segment, and the green dots represent the ground truth. So objectness is essentially defined based on the intersection over union between the segment and the ground truth. Now, given the segments and ground truth segmentation, we can have ground truth objectness for each of the segment, and then we can go ahead and train the point net to spit out an objectness score for each given segment. Now, each segment is assigned an objectness score, and we can go back to this hierarchy of segments. Our goal is to find the best segmentation, but so far we have only defined a local score for individual segments. We have yet to define a global score for the whole segmentation. It turns out if we score a segmentation by the lowest objectness score among its local segments, there exists a greedy algorithm that is guaranteed to return the optimal worst-case segmentation within linear time. We also propose an efficient algorithm guided by average K-score. Here we define a segmentation score by the average objectness score among all of its local segments. To evaluate how well the proposed algorithm segments point clouds, we follow the existing protocol to compute the percentage of objects that are under-segmented and over-segmented. This protocol assumes the output segmentation is a valid partition. On the left, we visualize an example of two under-segmented pedestrians that are merged into one segment. On the right side, we visualize an example of one over-segmented car, which is broken into multiple segments. Here, we plot segmentation errors evaluated on the KITTI dataset. We first show 4 baselines, featuring connected component with different single distance threshold, from 0.25 meter to 2 meter. As distance threshold increases, even though it's able to reduce the over-segmentation error as the middle column shows, it also causes more under-segmentation errors because a larger distance threshold tends to merge more things into the same segment. This supports the observation that there is no single one-fits-all distance parameter. As we construct a hierarchy out of the segmentations out of these 4 baselines, our proposed approach is able to adjust distance threshold locally based on the predicted objectness score of each local segment. The result is a much lower total segmentation error. We also plot the lower bound error for the given search space defined by the 4 connected component baselines. Comparing to our baselines, this lower bound uses ground truth objectness instead of predicted objectness. It reaches the lowest total segmentation error, showing there is still room for improvement in terms of modeling the objectness score of local point cloud segments. As we have mentioned before, there is no one-fits-all solution in terms of picking the best distance threshold for clustering. And the best threshold often varies from scenario to scenario. We presented an approach that can adaptively chooses the best distance threshold for each scenario locally based on a data-driven model. And here we visualize a video of results for our proposed approach. As you can see, sometimes our algorithm cannot solve the under-segmentation error between 2 pedestrians that walk side by side. This highlights one of the limitations of our approach, which is the performance is bounded by the search space. If there are no segmentation that resolves the under-segmentation within the hierarchy, our algorithm cannot recover that. Thanks for watching this video. If you are interested in learning more about this work, please consider checking out our website. Thank you.